let's imagine that we have a spherical shell. In other words, like a hollow sphere. Imagine like a balloon, but a very, very massive balloon where the skin of the balloon is very massive. And we have a radius of this as some radius r. And let's imagine that we want to figure out what is the gravitational attraction between this object and some object of mass m. Well, we're not going to do this exactly, but I will tell you qualitatively what it would look like and then what the results are. Imagine breaking this shell up into an infinitesimal number of little bits of the shell. Each one of those would create an attractive force on the mass. A little piece down here would attract it this way, a little piece up here would attract it this way, a little piece in the front would attract it more, a little piece in the back would attract it a little bit less. Add all these together, because of the symmetry, we expect that the total force would be towards the center of the sphere, so like this, towards the center of the sphere. But it turns out, it's an amazing result, that the total force that we end up with is the same as if the entire shell were a single point mass at the center of the sphere. We're not going to prove that, but it turns out it's done in the textbook. I think it's done in the textbook. Hopefully it's done in your textbook. It turns out that we can treat an entire spherical shell when we're outside the shell just like the entire mass were at the center. That is an amazing result. What if we're inside the sphere? So what if this mass is inside the sphere? Well, then it turns out little bits of the shell over here are going to pull it this way, while little bits of the shell over here are going to pull it this way. But these bits of the shell are further away than those bits of the shell. But there are more bits of the shell that are over on the left side than there are bits of the shell over on the right side. And again, it is an amazing result that the total force is 0. So inside the shell, there is no net force. There is no gravitational force. So as you come in, there is a gravitational attraction toward the center. It gets stronger, stronger, stronger as you get closer to the center. Stronger, stronger, stronger. But as soon as you pass into the shell, the force disappears. There is no more gravitational force inside the shell. An amazing, amazing result. What we're going to do is we're going to use this to imagine the mass coming in not to a shell but into a solid object like the Earth or another planet or something like that, going down through the surface. What happens? Let's take a look at that. Now let's imagine we're looking at some solid body, some spherical body, and we're going to assume that it has a uniform density, and we'll see where that comes in just a minute. When we are at a distance, so when the radius from the center to our object, when the radius is greater than the radius of the object, then the force of attraction is just what we've seen before. G, total mass, so the mass, we'll call this a capital M, times little m over r squared. So the force of attraction looks like this, just like we saw before. But what happens when r is less than capital R? Let's imagine we're in here at some smaller radius than the radius of the object. Well, what we saw before is that the mass outside this radius, so all of this mass out here, does not contribute to the gravitational force. The only force is going to be due to the mass that is within our radius r. Well, what's that mass? Well, let's call that m prime. So how much of the mass will be within our radius? Well, what we would expect is that the amount of mass will depend on what the volume is in here. Assuming we have a uniform density, in other words, mass per volume ratio, the mass in here will depend on how much volume we have. In other words, m prime over v prime, where v prime is this volume within our radius of r, should be the same as the total mass over the total volume. This is basically just saying the densities are the same, constant density. So m prime is going to be equal to the total mass times v prime over v. In other words, what's the ratio of the volume within our radius to the total volume v? Well, let's figure out what's that. So the total mass m, that's going to be times, what's the volume in here? What's the volume of a sphere of radius little r? Well, that's 4/3 pi r cubed. And what is the volume outside here? Well, that's a radius capital R, so that's 4/3 pi big R cubed. The 4/3 cancel, the pi cancels, and what do we end up with? We have m little r cubed over capital R cubed. That is the mass in here. So that the force of attraction then is going to be equal to G times the mass, but now we want m prime, which is capital M little r cubed over capital R cubed times the mass of our object, little m, and then divided by little r squared, because we are still at a distance of little r squared, or we're at a distance of little r from the center of this smaller sphere. So we still have to divide by little r squared. And what do we end up with? Well, we end up with G, big M, little m, over capital R cubed, but now we have a distance dependence of r. In other words, as little r increases, the gravitational attraction also increases. As r decreases, in other words, as you go in from the surface, the gravitational attraction decreases. So as you burrow down into the Earth, the gravitational force actually decreases because there is less mass within your radius. That's very, very interesting. So what is this gravitational force going to look like? This is r and this is f. At the radius r, outside r, we have a 1 over r squared dependence. So we're going to have something that looks like that. I've drawn it as negative because the force is always right in the negative direction towards the center, not in a direction of increasing r, but in a direction of decreasing r. But then when r is less than r, we have a 1 over r or a negative r dependence. So it's going to go like this, straight line, straight down, until these meet right there. And if we put r equals capital R, if we put in r equals capital R, we get G, oops, let's see, I hope you can see this. You put it over here. The force at r, if we use this result, we get G m over capital R squared. And if we use this result, we get G m big R over capital R cubed over R squared. We get the same thing. So both of these give us the same result when we are right at the surface of the planet, which is good. That's, we would expect, or we would hope, that we should get the same result when we're right at that boundary. So that's what it looks like. The force is 0 right at the center of the planet, and then increases, or becomes more negative. Remember, force is always in the negative direction, until we hit the surface of the planet, and then it starts to drop off as a 1 over r squared. And this is like r. Okay, very, very good. Wow, that was a lot. What we're going to start next is we're going to start looking at what happens when the objects that we're considering are not solid. What happens if they can flow? And objects that can flow are called fluids. So we're going to take a look at fluids next. See you next time. See you next time.